logarithmic functions. So we saw that how the chain rule helped us through exponential functions with other bases, so it stands to reason that we should be able to do the derivative of a logarithmic function with another base. Actually, this doesn't require the chain rule at all. However, like the exponential function that we just did, it does require us to convert the logarithm back into base e. So logarithms, being inverse exponential functions, are subject to the same rules for their bases. That is to say, the base still has to be a positive number not equal to 1. Well, like we saw with the exponential functions, we need to be able to convert this into base e, to the natural logarithm. Because we already have the derivative of the natural log of x, it's easier to work with. So, this is where the very simple change of base formula comes into play. For any logarithm with any base, the change of base formula says that we can use any other base. In this case, specifically, we want base e, the natural log of the input x over the natural log of the base. That simple. But again, what we need to realize is that a is a constant, which means the natural log of a is also constant. So I'm going to choose to write this as 1 over the natural log of a times the natural log of x. That way we have an entirely isolated constant factor, and then the natural log, which we already have the derivative of. So this is actually quick and very easy. The derivative of the logarithm base a of x is equal to the derivative with respect to x of 1 over the natural log of a times the natural log of x. Well, in a derivative, any constant coefficient carries straight through. And then the derivative of the natural log is 1 over x. So we have, quite simply, 1 over the natural log of the original base times x. So actually, again, much simpler. We don't need the chain rule here at all. We fit it all on one board without erasing anything. But once again, we see that scaling by the natural log of the base, just like we saw for the derivative of a to the x. So really what we're seeing is that whether it's the derivative of e to the x or any other base exponential, you basically do the same thing, you just end up scaling it by the natural log of the base. And here, again, we do the same thing. The derivative of the natural log of x is 1 over x, and then all we have to do is scale it by, well, in this case, the reciprocal of the natural log of the base. That reciprocal relationship between the scaling of the a to the x derivative and the scaling of the log base a of x derivative will actually be explained in more detail in the lesson on inverse functions. That comes up in a couple of lessons. But that's really all there is to it. It's you do the same thing for any base that you would do for the base e. You just end up scaling by the natural log of the base of the of the original base here, and that's all there is to it.